In this video, we're going to talk about circular motion that's taking place in a vertical plane. The biggest difference here from orbits is that you'll have the force of gravity, but you'll also have some other force, tension or normal force, that creates an overall net force causing that circular motion to happen. So to start us off, let's just redefine and remember what the different variables and equations are for circular motion. You've got linear and angular velocity. The biggest difference is linear is meters per second. Angular velocity is radians per second. Radius is measured in meters. P is the period, the time to go around once. And then you have acceleration and force. These are sometimes referred to as centripetal acceleration and centripetal force. For us, we're just going to talk about it as the acceleration that's happening in a circle and then overall force that results from that circle. So let's imagine, if you will, that you're swinging a ball on a rope above your head, and then all of a sudden the string breaks. This is a very simple scenario in theory because you have a single force that's force of tension causing that circle to happen, and gravity isn't necessarily playing a huge role in this overall. So in a top view, if that rope were to break, let's imagine it's breaking here. That ball is going to continue. It's no longer going to travel in a circle because there's no longer a force towards the center. And it's going to just send off in a straight line in whatever the tangential direction was to that circle that it was heading at that moment. Which means an inward facing force is required for circular motion. We talked about that before, that if there is an acceleration, there must be a force. That force is always pointing towards the center. So now, if you were to swing a ball on a vertical circle, where is that string most likely to break? Well, you may have some intuition about this. If you were to swing it, you will actually feel a pull that's a little bit different in different parts of the circle. Turns out that the tension required is the highest at position C. And the biggest reason is because gravity is pulling against the string at this point, but there still needs to be an overall net force towards the center to cause that circle to happen. So let's look at that. Remember, an object that follows a curved path has to have an inward pointing net force. Now, net force is not the same as other forces that we draw on a force free body diagram. So it's not like Fg, Fn, Ff, and Ft, which are forces that will draw directly on the object. This is an overall force that's a combination after those have been factored in. So this is a net force that basically results in the circular motion. F net equals mass times acceleration. Now, that means we can use all of our acceleration equations for circular motion that can then plug into that net force or vice versa, come out of that net force. And if you have a vertical circle and you have a constant speed, technically that's pretty hard to do if you're swinging around in that vertical plane. We are going to assume that the net force at all the points equals is pointing towards the middle. So this overall set of forces results in net force equals to mass times acceleration, and that net force is some force that's going towards the center. So that means if you were to combine all the forces that are acting at any part of this circle, the overall force needs to result in an overall net force towards the center. All right, I think this is easier if you see some specific examples and scenarios that we'll draw out. If you are swinging a ball on a vertical circle with a rope, the two most interesting locations are the highest point and the lowest point. So let's look at them. At the highest point, my net force is pointing down because the net force is always pointing towards the center of a circle. That's a rule that if an object is in or uniform circular motion, net force will always point towards the center. Then there are some other forces that are acting. There is a force of gravity. Force of gravity is mass times gravity. That's always pointing down. No matter where the circle is, doesn't matter. It always points down towards the center of the earth. And then here, there is also a rope. The rope is going to provide some tension. Tension, its rule for directionality is tension can only ever pull. So we are going to point tension in the direction that the rope is pointed. So that's also going to point down. And you can see how in this picture, Ft and Fg should add up together to give you that net force. At the bottom, we still have a net force. That force is pointing towards the center of the circle, which is now up. Um, we also have a force of gravity. Force of gravity is still down. Doesn't matter about the circle. Force of gravity is always down. Now the tension force for it to pull has to be pulling up. Now, if I look at this picture and I know that the net force is up and these forces are counteracting each other, I know that the larger of the two forces is the one that's pointing towards the center because the overall force, when they combine, must result in a net force towards the center. So Ft is going to be bigger than Fg by an amount of whatever the net force is. All right, let's put some numbers to this. So let's say that based on your circular motion, the net force required is 20 newtons, and the force of gravity on this object, certain amount of mass, is about 5 newtons. That means that we've got a net force at the top of 20 pointing down because that's where the center of the circle is. Fg is 5, and then Ft is unknown. There is no equation to calculate Ft. It's not something that you're going to find in the data booklet. You find it from the picture. So as we said before, Ft and Fg are working together to create this net force. So Ft plus 5 gives you 20, which means 20 minus 5. Ft has to be 15. It's whatever makes up uh, that combination to give you the net force. At the bottom, my net force is now 20 newtons up, and force of gravity is still 5 newtons down, but now we said Ft was pointing up. So 20 newtons up, Ft has to be bigger than Fg. There is no equation, you just look at the picture. Ft has to be 20 newtons larger than Fg in order for that net force to happen. So Ft ends up being 25 newtons. Now, the actual math to do these isn't very hard. The hardest part about this is identifying the problem and setting up your drawing in the correct orientation. So let's take a step back and actually calculate all the numbers here. Here we've got a ball that's moving around. We're going to assume, again, uniform circular motion. So this ball remains the same 2 kilograms and has the same velocity at the top and the bottom. This velocity is meters per second, which means it's v, the linear velocity. R is the radius, so the length of the string is 0.5 meters. We can calculate the rest of this. Net force, remember, is just mass times acceleration. There are a lot of different ways we can calculate acceleration for circular motion. There's only one that contains v and r in it. So acceleration is v squared over r, which is 5 squared divided by 0.5, which is 50. So 2 times 50, the mass times the acceleration, gives you a net force of 100 newtons. That's the same at the top and the bottom because the velocity is the same, the radius is the same in both of those locations. Now, Fg is the force of gravity. That's just mass times gravity, gravity being 9.8. So 2 times 9.8 is 19.6. That's the same on the top and the bottom because it's the same mass, 2 kilograms both times. The only difference here is going to be Ft. Ft at the top has to combine with Fg to give you your net force, and at the bottom, Ft has to be larger than Fg by the amount of the net force. So you'll find at the top Ft is 100 minus 19.6, which is 80.4, because 19.6 plus 80.4 gives you 100. And then at the top, you have 119.6 because 119.6 minus 19.6 gives you a net force of 100. This also checks with our answer that we talked about before, where at the bottom, the string is more likely to break. It is experiencing a higher force of tension for the same amount of velocity because it is fighting gravity. All right, another scenario for this vertical swinging around a circle. You've got an angular velocity. You're trying to find an angular velocity in radians per second at the bottom of a vertical circle created when a 0.2 kilograms cell phone charger is swung with a 0.8 meter cord and a tension of 6 newtons at the lowest point. Great place to start is draw a picture. So we know that there's a net force up because that's where the center is. We know that there's a tension force up because that's the direction that the rope is pulling. That's 6. And we know there's a force of gravity down because that's where the center of the Earth is. I know a mass, so mass times gravity, 0.2 times 9.8 is 1.96. This is enough for me to calculate a net force. So before we started with net force, here we are working our way toward that. Net force is just the tension minus the gravity, 6 minus 1.96, which is 4.04. That net force can be helpful because net force is equal to mass times acceleration. I want to know an angular velocity here. So while there's a couple different equations that we could use, we used v squared over r last time. Angular velocity is omega. That's this little W symbol. So I'm going to use that part, that equation, a is equal to omega squared r, as my radius or my acceleration. So m times the acceleration, omega squared r, I can use for my net force. I know the net force is 4.04, the mass is 0.2, the radius is 0.8. which allows me to calculate omega as being just over 5 radians per second. So sometimes, like we saw in the last problem, we have information about the motion that we can find a net force and then use that net force to figure out any unknown forces. Sometimes, like in this one, we know everything about the forces. We use that to find a net force to work toward acceleration to basically define the motion with our other motion variables. All right, another type of circular motion that happens in a vertical circle isn't because of tension, but because of a normal force. So as a reminder, normal force is a surface that is pushing on an object perpendicular to the object or perpendicular to the surface as it's acting on it, which means if you were to tilt a table, the direction of the normal force changes, but notice how FG did not change. Now, there are some other things that would change about the length of those vectors that we're not going to worry about, but in terms of purely direction, Fn can change, but Fg is still going to be going straight down. So if we imagine that you're on a roller coaster that's at the bottom of a dip. Now, this isn't a complete circle, but we can pretend that it's part of a circle and basically define this using the same circular motion rules that we have already. We can draw a free body diagram representing what's happening here as it's going on this circle with a radius of 8. So here's my car, the object. I know that there's a net force that's acting here. The net force has to be up because remember, the net force is always in the direction of the center of the circle. So since I'm at the bottom, net force is going up. I have a equation. I know that net force is mass times acceleration. In this case, that's going to be helpful for me, most helpful to call acceleration v squared over r because I know v and I know r and plug in my numbers, I'll find that whatever it is, this net force has to be 2,500 newtons. Okay, now where does that net force come from? Well, it's a combination of a couple of forces. There is a force of gravity, and there's a normal force. This normal force is the surface pushing on the car. Since the surface is below the car, it pushes the car up. I can calculate some of this. I can calculate the force of gravity. 200 times 9.8 is 1960. Now, there is no equation for normal force, nothing that you're given, but you can use these numbers to figure it out. You know that the normal force has to be larger than the force of gravity because the net force is in that direction. And you know that it needs to be bigger by the amount of the net force. So another way to say that is the net force is just Fn minus Fg, the bigger one, minus the smaller one. I can plug in my numbers um, and basically rearrange. Fn is just Fnet plus Fg and I can find Fn is 4,460 newtons there on the bottom. If my roller coaster is at the top, I can do the same sort of calculations here. I'm going to approximate a circle. Let's call that 8 meters as well. Now you'll notice I am moving a little bit slower, 5 meters per second. My net force is also changed. My net force is going to be moving down because I'm at the top and the center of the circle is downward. There is a force that I can calculate for net force. Again, it's just mass times acceleration. Acceleration being uh, v squared over r, and I can calculate that is 625 newtons. So whatever the other forces are, the combination needs to be 625 to create this circular motion that I know is happening. Fg is pointing down. Fn is still pointing up because the surface is on the bottom of the car, pushing it up. Now, if I look at these, I expect Fg to be bigger than Fn because Fnet is pointing down. So Fg is the same 1960. If Fg is 1960, Fnet has to be 625. Means Fnet is the bigger one minus the smaller one, Fg minus Fn. So Fn is 1960 minus uh, 625 to give you 1335. Okay, so for each of these, I was able to calculate Fn by first understanding what the normal or the net force was, and then just rearrange, make my picture, and solve for the normal force. Now, that normal force is important. It turns out that normal force is basically what you perceive as your weight. If you're sitting in a chair right now, your weight is pointing down and the normal force is pointing up. But since you're not accelerating, those two cancel each other out and you have the same, your normal force is the same as your weight. So that is kind of our baseline for how we feel we weigh. If you're in a roller coaster, though, where you're at the bottom of the track, you'll notice that the normal force is higher than 1960, what the weight actually was in this case, which means you basically feel squished into your seat. Your perceived weight is heavier than it would be otherwise, because Fn is larger than Fg, being squished in. Sometimes roller coasters will call it pulling G's. Basically, some multiplier of the force of gravity is what you are feeling. At the top of this, you'll notice that your normal force is smaller than your force of gravity, which basically gives you this feeling of being weightless. Now, are you weightless? No, you still have a weight. That's 1960. But your perceived weightlessness is really a normal forcelessness. It just doesn't roll off the tongue as much. Basically, what's happening is the seat doesn't have to push on you as hard when you're creating that motion, and you feel lighter than you do before. Okay, the ultimate example of this is something called the Vomit Comet or a zero G airplane. It's basically an airplane that goes in these swooping parabolic arcs. When that happens, yeah, it's actually moving fast enough and tracing a sharp enough circle that the net force pointing towards the center of the circle ends up equaling the force of gravity, which means the normal force goes down to zero. If you have no normal force, the surface that was maintaining contact on you doesn't necessarily need to maintain contact, and you start floating. Um, but it means at the bottom of this, your net force is pointing upward and your force of gravity is down. Your normal force ends up being twice as much. So you pay for it on one side, but you can get these really cool parts where basically you're experiencing weightlessness. People can float around, astronauts can train for what it's like to feel like being out in space. All right, one more example of a circular motion that's in a vertical circle, and that's the loop-de-loop. This is a little bit different than our other roller coasters because here, when you're at the top of this track, you know that the net force has to be towards the center, so that's down. The force of gravity is down because force of gravity is always down. But now, since you're under the track is a surface that can only push. So the normal force ends up being down as well, which means just like we saw with the rope, we have a normal force and a force of gravity instead of tension and gravity that are combining to give you a net force. And we can look at this in basically like worst case scenario. What is the slowest speed that you still stay in your car? So if you've ever ridden one of these loop de loops, you feel like you're squished into the seat even when you're upside down. And that's because of the circular motion that's happening. Now, if you go up to the top, um, there is a situation that you'd be going so slow that the normal force ends up equaling zero. So to get that net force going towards the center, all of it has to come from the force of gravity. That's the only force that's acting if your normal force goes to zero. This is the slowest possible speed, the worst case scenario. And we know some ways to calculate that. We know that the normal for or the net force is mass times acceleration, and we know the force of gravity is mass times gravity. And then we know that acceleration can be calculated if we know how fast you're going. It's just v squared over r. So we set m times v squared over r is equal to mass times gravity because net force is all from Fg. And if I do this, I'll see that m is on both sides, so I can cross that off and then solve this for v. V in this case is essentially the minimum velocity that's required. So this is how slow you'd have to go for normal force to be zero, and you can't go slower than that or you'd fall off the track. If I rearrange this, I will get v is equal to the square root of g times r, which is kind of wild that the minimum velocity required doesn't have to do with the mass at all. It is based entirely on the radius of the circle that you're trying to make. Uh, that will tell you how fast you need to be traveling at the highest point to maintain contact with the track. All right, some takeaways. You should be able to compare the forces that are acting on an object at different positions in vertical circular motion. You should be able to determine the magnitude and direction of the forces needed for the overall centripetal force, basically understanding that the net force is always towards the center. You should be able to qualitatively describe how the tension force is in a vertical circle. So you know that down on the lowest part, the tension is greatest, and also be able to qualitatively describe how the normal force changes in a vertical circle. So when you feel weightless or lighter, when you feel heavier, and then be able to describe this experience of weightlessness, essentially normal forcelessness, in terms of that idea of a normal force.